They lost a representative in the last survey.
Artie, this is Casey. We cannot hear it.
All right. Good morning, everyone. Maybe can I get a quick audio check from Zoom? Can you hear us now? Okay.
Yes, now it's okay.
Yeah, now I can hear. That's great.
Okay, great. All right. So, well, welcome, everyone. Let's go ahead and get started. We are very pleased and honored to welcome Dr. Tom Frey to George Mason University. He tells me it's his first time on campus. So, welcome, Tom. I'd like to just give a quick introduction for Dr. Frey, and then we'll kick things off or learn about information fusion in F-35. So Dr. Frey is a Lockheed Martin Senior Fellow for Information Fusion. He led the design, development, and integration of F-35 sensor fusion capability into the F-35 Lightning II program. He has published over 30 technical papers, contributed to 2 chapters to a recently published book on beamforming and advanced antenna design. Currently, he's developing distributed network of collaboration technologies based on stickmergic principles. Dr. Frey is a fellow of AIAA and a registered professional engineer. He sits on the Industry Advisory Board for Electrical and Computer Engineering at the Texas A&M University. And he's the chair emeritus of AIAA Sensor Systems and Information Fusion Technical Committee. And in addition to that, Dr. Frey has been just a great mentor and a great person to chat about all things fusion and information fusion related. And he's often humble about it, but I would say that if you read about the F-35 information fusion capability, the DoD and a lot of folks that pilots who use F-35 or fly F-35, they say fusion is one of the core capabilities of that aircraft. A lot of times when we're thinking about an aircraft, we think about speed, agility, stealth. Fusion doesn't come to mind, but the way this F-35 program is, the ability to fuse information is one of the core capabilities for that platform. And Dr. Frey has really led the theoretical developments and then its practical implementation into the system. So please welcome Dr. Frey, and then the floor is all yours.
Thank you so much. Would it be easier for me to sit at the end of the table and look this way into the camera, or just what works best for you? Anyway, let me do.
Yeah, let's do
let
that.
me just
Yeah,
swing around
yeah.
here. This will see me. I can use this as my display. I'll steal your camera from you. Good morning. I'm very pleased to be here. This is my first time at George Mason University, and I really have enjoyed it so far. Just a beautiful campus and beautiful weather today. I'd like to take a little bit of time today and talk to you about the F-35 fusion solution that we had. I can say this without exaggeration. It is the most capable fusion system on any tactical fighter ever. It was the first fighter aircraft to fully integrate not just all the onboard sensors, but all the offboard information as well. On most aircraft that came before us, they chose between an onboard or offboard solution, chose the best one. We fully integrated, which allows us to combine that data and leverage all the spatial information involved with that, plus to take the partial ID information available from all the different pieces to combine them into a representation of the entities in the battle space around us. And so we're going to try to go through that in as much detail as my lawyers will let me get away with, but I won't tell them if you don't tell them. So this presentation actually came from an AIAA presentation series that was done on the F-35, from cockpit to, or from concept to cockpit. We went through all the systems and their development. So people,
panel?
oh, sure, thank you. So people often ask me, particularly my mother, what is fusion? And so I took this quote from several of the fighter pilots out at one of the different bases as they describe this, as they're testing the system. And from their perspective, fusion is a hardened, smart networking capability flying into a heavily defended airspace, collecting information about ever-changing defenses, finding and automatically prioritizing multiple targets in the air and ground, even as they change, and sharing that information with all the other weapon systems, both F-35 and other things, all while going up to Mach 1.5. The F-35 is a single-seater, which means that the machine has to do all this to the pilot. So the pilot's not queuing the systems have to know when to queue themselves to go get this sort of data. The single seat really forced this autonomy onto our fighter aircraft. And so that, I was telling Ali earlier that the Air Force pilots were the first ones to really trust automation in their aircraft. It was really because they had to do their mission. The pilot couldn't both fly the airplane and cue the sensors and try to interpret what all the sensors were telling them. They needed the system to do it. And so fusion needs to interact with the environment to detect, combine, prioritize, and cross-cue all the sensors. These are the normal functions we think of as correlation, estimation, identification, sensor management. By the way, if you have questions as we go on, please feel free to type in. I'm happy to answer them. Is it just slow or am I not hitting right? Ah, it was just sleeping. Okay, so I have to hit again because there's a box that pops up. There we go. So we have to provide the data to the pilot in a way he can easily orient himself to the battle space and then take the actions he needs to take with his aircraft, make his mission level decisions. One of the ways that tactical aircraft are different than surveillance fusion systems is the pilot is going through this right now. He can't come back next week and figure out if he was right or not. He lives or dies with the information he has now. And so we can't passively sit back and just listen to what the environment gives us. We go out and actually have to interact with it to quickly determine that's a threat, that's not a threat. This is within the sphere that you need to be worried about. This one's far out. We'll just keep our eye on it. And so the systems on our tactical fighters, particularly the fifth generations, are very interactive and are out to quickly identify what's out there so the pilot can understand the situation and decide how he wants to handle that. This also causes fundamental design decisions on different systems. The surveillance system and the tactical system have different design decisions on how they implement their fusion. And they're all based on different goals, whether to bring everything back and then to analyze it and discover new things, or to understand the situation as quickly as possible and throw away things that aren't important to what I need to do right now. And so there was this one idea that there's one fusion ring to rule them all, sort of like the Ring of Sauron. But actually, there is no one golden fusion system. Every system has decisions that are designed for their missions. And there are two fundamental different designs between the tactical and a surveillance type mission. But let's get down into details because everyone wants to talk about details. So if you look at the evolution of fusion technology in aircraft, and I'm going to stick just to tactical aircraft for this. Back in the early 80s, actually before the 80s, back in the 50s, there really was only one sensor you get on your aircraft. It was the radar. It was the only thing that had any sort of directivity to it. And so the radar was it. It told you everything. You didn't need any fusion. The radar told you where everybody was and what you wanted to do about it. As we started getting into the 70s and 80s, we began to add ESM sensors that were no longer just quadrant based, like back here someone's trying to hurt you. But now start having some accuracy to it. And we had data links. Now someone else's radar can come into you. Well, now the pilot's seeing multiple tracks for the same entity in the environment. And so we needed some mechanism to begin to unclutter his display. So we introduced correlation to it. Now remember, these are the days of the screaming 1 megahertz processors. For those of you old enough to remember that, for others it may seem like a myth, but truly we thought we paid $4,000 for computers that had that screaming 1 megahertz processor. The price of computers never changed, just as speed goes up. And so correlation was a big thing. So you would do it, and then you would find out, okay, all these guys belong together. You pick which is the best track, and you would display that track and just press the others. And that was the first step of this. We call it display fusion. As we began to add more to it, we had sensors. Maybe I had an IRS-T. I wanted to get used to those better angle accuracies that my radar had. And so in the 80s and on the F-18, for example, we started to move to some sort of, if not estimation, at least dimensional combining. They call it track blending. For those, we would take the best measurement of each sensor and actually sort of a weighted sum of these. So we had some idea of sort of the best aspect of the track. It's not true estimation. There was no estimate of the future state or current state. It was just sort of in each dimension, take the weighted average of all the different measurements. And that gave you some ability to have a little better track to pass forward. And so we did with that for many years. And that was sort of the track blending. We were still doing track to track correlation. And that's because our sensors just were already existing. We're adding fusion onto it. And so we would just have to take whatever the sensor gave us and combine it. Starting in the 2000s with the 5th gens, the F-22, and then later the F-35, we began to see the benefit of actually using the measurements from the sensors to get even more accuracy to it. We began to start doing now the correlation based on the measurement data for better correlation behavior and estimation, true estimation. Our processes were getting faster. We began to do estimation based on those measurement data, and that allowed us to get more accurate tracks and to actually do some of the predictive type work that we want to do for supporting weapons. And so this is sort of how we moved along the track over the years. So, for tactical things, as we got more processing speed, we were able to do more things and bringing more of our theories into practice on these aircraft. The F-35 particularly kind of went beyond everything before it. Up to the F-35, we had data links, but you chose between the data link information, the onboard data. You chose the best one, that's what you used. You never combined it. F-35 said, no, we're going to use all the data. We're going to use the measurements I get, the measurements my wingmen get, both ranged and unranged, so we could get a real good picture of what's going on in the environment. So it used the measurement-based sensors, the autonomous sensor management, the ability to go out and interact with the environment in real time to gather what's missing. It's actually the first aircraft that provides ID estimation with confidence, but no a priori data needs. So it's not a Bayesian where you have to define the densities of all your targets being in the environment before you take off. It actually uses an evidential method. And so it provides the pilot not only with the estimate of ID, but the probability of that ID. And so that was something the pilots really loved, being able to know not just you called it this guy, but how confident are you, and the ability to see that and use that. We had the collaborative sharing, which actually caused a bunch of innovations we had to make how to pass around that data. And then finally, we had some innovations I'll talk about a little bit on how to share data between F-35 such that it could be shared with anyone. It didn't depend on your fusion algorithm, it was agnostic. And we were successful at demonstrating some of that, porting the data off the aircraft to other systems so they could translate their own data and use it like it was a remote sensor to them. And we'll talk a little bit about that, why that was important. Am I going too fast? Is this okay? Okay. So before you can talk about fusion, you have to talk about the tools that fusion gets to work with. Fusion may be the brain, but it needs smell and touch and hearing and vision. And so this is the avionics suite of the F-35. It has 5 major sensors. The first is the radar. which has an actively electronically scanned array, which means the array doesn't move. It electronically forms beams wherever it needs it. It provides both active radar and passive ESM type capabilities. We have an EW system, electronic warning, which covers 360 degrees around the aircraft, detecting emitters out there. It provides both a basic warning and a fine measurement. It also supports multiple types of ranging techniques that we can use to geolocate emitters on the surface. We have two different IR systems. One is an electronic or electro-optical targeting system, or EOTS. It is a scanning of a FLIR, essentially. It can be used in an air-to-air mode or an air-to-surface. For air-to-surface, we use it for locating things on the ground. It also provides an image. You can ID visually a target there. It has a laser associated with it for targeting, etc. For the air, also, you can have it search a pattern, or you can lock it to the next shoot or the system point of interest. So you can have it either slave to some place you're already looking, or have it work its background search. The second IR system is called a DAS. It's an electro-optical distributed aperture system. It's a 4-pi stir radiant, originally planned for missile warning, but it provides visibility in all directions for IR, allows us to see things out, particularly hot things, pretty far. It also provides the pilot with a IR representation. He can put in his helmet, actually look at images, look down through the bottom of the aircraft at the ground. And so it's another tool he can use for navigation. And then finally, we have the Cni system, the COM navigation identification system. This has all your IFF, all your data links, as well as all the navigation systems for the aircraft. Our apertures for both EW and Cni systems are located on our leading edges. You can see those, I wish I was colorblind, they may be orange. It says band 2, band 3, and 4 apertures, both forward and aft. So they all look 360 degrees around the aircraft. And so these are the inputs I have come into Fusion: radar data, directions to emitters, IR data, data links, IFF, other sorts of data link data. All right, so let's see where we go from there. So on the 5th gens, because we got designed Fusion with our sensors, we were able to make sure that the sensors provide the data that was best for Fusion. So we get information about the measurements themselves instead of tracks. We also found ways to cue the sensors better to help them quickly respond to what we want. One thing we do is all the sensors send us their tracks along with their measurements. We then prioritize all their tracks based on the system priorities. So when a sensor gets overloaded and doesn't have enough track space, it starts to get rid of tracks based on the system's priority, not the sensor's priority. So always sure that we're all paying attention to the same, the tracks are most important to the pilot. We provide an integrated view of the environment. Some of the core aspects as our architecture is actually designed to be extensible. So even though it's implemented on one tiny processor, it was actually set up and designed to be able to spread across multiple ones, which we're starting to do now as processors get faster, we get more of them. We do this data sharing across the platforms. We'll talk in some more detail about the evidential ID algorithm. We'll talk more about sensor management and collaborative sensing. Now that we're fully connected to all the aircraft, we can do things like TDOA and angle ranging just as a natural course. No longer for the pilot to command it just happens. All right, so let's finally get to the picture about Fusion. We've talked all about this. This is sort of a cartoon, but it sort of gives you the top view of the architecture, and it turns sort of like an OODA loop. I think most of you are familiar with the concept of OODA loop. You observe, you orient yourself to what's going on, you decide how to act, and you take that action. And then any sort of conflict, what Colonel Boyd postulated was, in any conflict, the pilot who can turn that loop the fastest has the advantage because it's reacting. The other person is having to react to you instead of you reacting to them. And so we run this sort of like a huge OODA loop. On our far left, you see we have our sensors, our onboard sensors, and then our offboard, our data links, whatever someone else We run that through a thing we call virtual interface models. And this is sort of a C++ type thing to encapsulate the complexity of Fusion inside of Fusion and remove the complexity of the sensors and interfaces from Fusion. So it sort of makes it easier to add new data links and new sensors because there's a standard way we take data into Fusion and the BIM just provides us that data. Maybe taking the last nav data, appending it to that data. So when we get the package, it's all ready to go through Fusion. So it's a way to kind of create that isolation variable. Once that data comes in, it goes through data association. As all of you know, have ever tried this, data association is the thing we ignore when we write papers, but is the most critical part of any system. If you can't put the right pieces together, you're not going to get the right answer, and you may not be able to get rid of the bad data. So it's probably the most important piece of any Fusion is solving the correlation problem. Once you decide the pieces go together, the next step is then how to use that data to estimate position, kinematic estimation, estimate the ID of that entity, and then something we use a lot in aircraft, the rules of engagement. Those are, what do you have to know about its kinematics or ID to allow it to, for you to declare it as a friendly, as a hostile, as a suspect. These are legal definitions that are different from ID. And so there's a separate process that allows us to do that. Once that information is done, it winds up in the system track file. From the system track file, we have another virtual interface model we call the Fusion server. And so it isolates all the Fusion data from all the consumers of that data. This is really important. An aircraft, a legacy aircraft, kind of just put out the system tracks to the world. It's kind of like mom's cooking. I'm making it this way, everyone's going to get the same data. Well, if you want it different, you had to doctor it up yourself. But when Fusion got a new message or added new data, every system had to change because its message changed, which meant everyone was affected by it. So it was hugely expensive to change Fusion in any way. Having a Fusion server, it's sort of like your Instacart. It will go out now and build your message the way you want. As long as the data is in the system track file, you get your message. System track file can add new data, but it doesn't affect your message. Also, if we want to add a new consumer of the data at the end, the Fusion server, if all the data is already in the system track file, the software changes just in the Fusion server. It doesn't affect Fusion whatsoever. It's again a way to isolate the two pieces and make changes easier to do and much less expensive and much less disruptive. But finally, the sensor management system closes the loop by evaluating each track, figuring out what sort of information we need to know about it, and queuing sensors to go out and provide that data. It's constantly reevaluating each track to find out, does it meet the content and quality we need of that track? All right, I may be going a little fast, but here we go. So one of the key innovations of the F-35, if we're going to start sharing data across platforms, first thing we have to consider is how are we going to ensure that we can use the data when it arrives? I'd like to use it like it's independent. How do I make sure that the data I get from my other F-35 is independent data? I'm not just getting the same data through a different data link or a different message. And so we knew that was really important to being able to use the data. And so we came up with this concept of tiered data. We had this idea of tier 1 data. So every track has two tiers, two-tier representation. Tier 1 is it's the representation of that track's position based on only my onboard sensors. So I have one version that's just all my onboard sensors. This is the position it predicts for that track. I then have a tier 3 solution that says, for all the onboard and offboard data I have, what is my best estimate of where that entity is? And so the tier 3 solution is what we would normally think of sending out. That's what I share with my pilot and all the consumers. But when I want to go share my data across MATL to my wingman, I share my tier 1 data. Why do I do that? I do it because that information is guaranteed to be independent. And so on the other end, I can use it because of its independence. And if I have to send a tier 3 solution, sometimes it's all I have. I'll select a certain bit to tell the receivers, this data is tier 3, it needs to be handled differently in the estimation process. By sending the tier 1 tracks across, on the other end, I can use a technique called tracklets, which I'm sure many of you are familiar with it. Essentially, what a tracklet does, it takes 2 successive track updates and says, what is the effective measurement that would have caused the track to go from the previous state to the current state? And so you could basically solve for the equivalent measurement. Well, that equivalent measurement is just like a measurement on your sensor. It's independent, and you can put it straight into your filter. And so it's kind of a real neat trick. I talked earlier, we did this to be fusion agnostic. When we did some early experiments with the Aegis out in the desert, we were passing data into it like remote sensor. We received the MATL messages in tier 1s. We then took it to a ground site, and we converted that using a tracklet into measurement data and fed it to the Aegis system like it was its own radar getting the data. It used that data like its radar to guide a missile, and we had a successful kinematic kill out in the desert by doing that. No changes to an F-35. The F-35, the Marines just flew over the site to help out. The Aegis was the one out in the desert. In fact, the Army was really pissed at us. They didn't expect us to hit it, so we destroyed one of their drones. Things happen. But the idea was this allows data to be easily shared and turned back into the type of data that a fusion system would want to receive. We've done the same sort of thing with the ballistic missile type things. We're doing some tracks on launches out of Vandenberg, just showing how this data could easily go into other networks and be used easily by another fusion system. So this was a technique that we selected because we saw it the easiest to share with other networks that weren't us. We wanted something that would easily help us integrate new networks in the future. Okay, I see my time driving away. I'm PhD, I'm long-winded. I apologize. So let's talk a little bit about the ID piece. The guy that we had work in our ID portion was Kent Engelbrecht. He was Air Force Academy grad, used to work for the Air Force testing all our contractor ID systems, used to complain about how short-sighted we contractors were. So we hired him and said, okay, make the right one. And so he did. He went out there and he used a modified Dempster-Schaefer algorithm, okay, which meant that we didn't have to know priorities from the data. We just need to know how well our systems work. And from each piece of data, we were able to build up confidence in our IDs. This picture down the bottom left, this is actually a representation of one of our early flight test pieces. This not only provides an estimate of the ID and the ambiguity, it also gives you a confidence to go through it. This algorithm provides you a way to express confidence for this. And it's modified in a way that we actually use probabilities and not belief masses, which is the standard Dempster-Schaefer piece. If you look down here on the top row, that's the affiliation row. In this case, it says it's 0% hostile, 0% neutral, and 100% friendly. In a second, I'll tell you why we know it's 100%.
Can you just show us where you're pointing to? Because is it that image number 2?
So I'm looking at the image number 2. It looks like a cockpit display.
Yeah.
And on the bottom, there is a piece that shows up that has some writing and then has different color text after it. The pilot calls that the bark box. The tech writers call it the expanded display. But so the first row of that just deals with affiliation. We're trying to decide if it's friendly, hostile. It's the ROE type affiliation. In this case, it's 100% friendly. You see the F and then 1.00, 100%. The next 2 rows work together. That's the fusion ID and then the confidence of that ID below it. In this case, we know it's an F-35 100%. And there are no other ambiguities, so there to just say unknown 0%. Underneath it, the next rows are the sensors that contributed to that ID. And this was something the pilots wanted earlier to get their belief in the system. And so in this case, it's a MATL PPLI. Well, since it's a MATL PPLI, it's for certain an F-35 because that's the only thing we could talk on a MATL today. And then Link 16 did not have a category for F-35, so it was just an unknown fighter. And so in this case, we were testing out the PPLIs of Link 16 and MATL. And so in this case, MATL, both knew it was a fighter, but MATL knew it was an F-35 100% For other targets out there, you may see other IDs and their confidence below it, but it's a way for the pilot to very quickly get out and see what the system thinks is and how well it believes that. The pilots became so comfortable with this halfway through flight test, they asked if we could have a filter to close that. They no longer needed to know anything beyond what the IDs were. They trusted the system. It very quickly was adopted. And so this has been overwhelmingly successful. We've looked at how to put it back in some of our legacy jets now to go and do that.
Sorry,
Go ahead.
the color codes, can you say a little bit more about that?
So
What does green mean and what does red mean?
thank you. That's a wonderful question. Although I'm colorblind, the green is friendly. The red is hostile. If we had a yellow, that's suspect. And white is unknown. And we're going to use that. I have a sort of an example at the end that we'll talk through, and the colors will be very important. It turns out for symbols, this one doesn't have the right symbols on it, but friendly symbols, air symbols, are green circles. Hostile air targets are red diamonds, etc. And unknowns are white squares. Well, for that. One of the final pieces of this was the sensor management piece. Unlike a lot of, differently than the stranded systems, the F-35 and the tactical aircraft need to interact with the environment. And so the question is, how do I embed my mission goals into that so my system best uses the sensors to get the information it needs? Dr. Ensley, who was at Texas Tech in the 70s and 80s, did a lot of studies on situational awareness for different things, one of which was tactical aircraft, and came up with these ideas of these decision boundaries of the pilot's mission. You have this long range piece where someone enters your sphere of influence. You need to know a certain amount of data about them. It's still a two-dimensional world. You're way far out there, but things you want to know, are they friendly or not? You want to sort of range an angle, just so you know when they start to get closer to you. As they get closer, there's another boundary. That's your situational awareness boundary. There's a second boundary where now they're starting to get close enough to you. You need to know more about them to figure out how dangerous they are to you, what you want to do about it. And so this starts to become more of a three-dimensional world. And you want to know more information about this target. And so on the F-35, we have these two primary boundaries that we define: this SA boundary and tactical boundary. Outside the SA boundary, we want to know you're there. We don't want to lose you, but it's just sort of bookkeeping. Once you enter the situation boundary, there's certain information we want to know about you kinematically and ID, so that we can make some general decisions about, where the bad guys are, where things are happening. Inside a tactical boundary, we kind of want to know everything about you. We want to be prepared if we need to go engage to understand that. All this should be before you ever see me. And so by having these decision boundaries and the information we need at those, we can now decide what we need to know about each track. Now this shows basically the radar field of view, but this actually goes 360 degrees around the aircraft. It happens, there are boundaries both in the aft as well as in the forward quadrants. We also have a different one for surface targets as well, or surface tracks. But this is sort of the magic of how you figure out how to use your sensors wisely. We don't look for the best information. We look for sufficient information. If I need to know to 1 degree, if I get 1 degree, I want to spend sensor timeline now going to bring someone else up to 1 degree, where I try to get you to half degree. And so this idea of sufficient information was very key to being able to make good decisions and to get more targets refined inside the environment. Okay, the final piece I'm going to talk about is the collaborative sensing, and then we're going to do a little thought experiment. Collaborative sensing, I don't know if you read, there was a press release about 5 years ago where one of our competitors put 2 IRCs together and was able to passively range a target, flight test. And of course, my CEO immediately sent me an email that said, "They can do that. Can we do that?" And so, the email went back up and said, "Very good. They did one-on-one. We can do all on all." And she felt better then. I didn't get another email back. But it's part of the, one-on-one for all you guys done simulation, one-on-one's nice and easy, right? What happens when one guy sees 5, one guy sees 7? Well, you get all these false intersection points. Which one's the right one? And so solving that becomes the real problem. And then when does everyone see the same picture, or as much as they're going to see, so you're allowed to solve the problem? And so those are some of the kind of tricks. How do you solve that? How do you solve them quickly? All sorts of interesting ways to do that. If you have RF information, it solves a lot quicker because you have another dimension that you can throw away combination or ghosts. The other thing we're able to do now, because I can coordinate my sensors on my wingman, we can do TDOA. And so it's easy for the system to just do it. We have a new ground sign beam at this accuracy. Let's schedule TDOA. I tell my buddies, they schedule to go collect data and we're done. And so the ability to collaborate what we're doing to work together to do these different things, where it's angle ranging or TDOA, the ability to collaborate like this makes us much more efficient getting through the environment. I assume everyone's very familiar with TDOA, looking at time difference of arrival of a pulse of 2 different observers. That gives us lines of constant time or constant delta time called isochrones. If you get 2 or more independent isochrones, they intersect the position. Now you have a horizontal position. Intersect that with the Earth, you get elevation, and now you can place on the Earth pretty accurately. And so all of these happen autonomously in the aircraft. The pilot can cue a TDOA, but he doesn't have to. The system does this all automatically. All right, I've kind of rushed you through a bunch of this. I would love to talk to you for hours about each one of these, but most of you, I probably would have bored you. For those others, we could still do that at a future date. So we're gonna do a thought experiment now. I'm gonna actually put a scenario up there, 35 targets in this scenario. And I'm gonna show you what each of my sensors see. Then we're gonna look about what goes into fusion. We're gonna look at what another fusion system might see, and then we'll see what an F-35 might see. So we talked about the symbology earlier. Green circle is friendly, red diamond is hostile, and those are the only, I'll use that in unknown, which is the white square for this. Because it's EW and these are emitting, we put a little dish on it. The dish just says the target's emitting. And so if I looked at my EW system right now, I would get essentially lines of bearing. These are all the reports I get from my EW system. I see 22 people out there. So 22 of the 35 are emitting this environment. And we call this just a gutter. They just sit out at no uncertain range, just let you know these lines of sights are out there. But I have ID on them, so I know they're friendly or hostile if I could just put them with the rest of the information on my aircraft. So I have my radar. My radar looks out and it sees these things. It has no ID, so they're unknown for what my radar sees. The stick coming out the front are velocity vectors. So they represent, we have an estimate of velocity of that target. And so well, the radar sees a little bit, but the radar is not giving me a big view of the other 35 guys out there. It's got 6 of them. So my R is doing pretty well. It sees them all. I've got hotspots of all 35. So that's great. So now from AW, my radar, and my IR, can you see where all 35 targets are again? I have a tough one, isn't it? Well, let's bring the data link. Let's get some help from my buddies. So now my buddies tell me where they are, and they also tell me what their radars see and what they're able to view. So now, from the pilot's perspective, for the F-35s, I am getting angle-only data, but right now I don't have a way to explain it to my pilot yet. I just know there's angle-only data coming in. And so I'm getting more of the environment, but I'm still not getting it all. These red or the green lollipops are friendlies. Normally I'm getting those from some sort of self-reporting. You can see they have a velocity vector with them as well. All right, so let's put them all on one chart. This is all the data that's going into future. And so the idea is lots of data. Some of these, it's obvious they belong there. Some of them not quite so much. So let's take a look at what a track blending might do. This is sort of one of our legacy aircraft. They're going to take the things that were ranged and they're going to put those together pretty well. And then often what they'll do is take the angle only that's closest to line of sight, declare it that's the angle only that should be with that track. And they're right sometimes. And they're wrong a lot of times. And because they do that guessing, they get the ID wrong sometimes, and there's no way to stop it. So they have to make the IDs either break when it no longer correlates, the ID goes away, or they have to have a system that degrades ID over time. So you have to keep updating ID. So if you get it wrong, it eventually fades out. Try again. Not very good for the pilots. They're not very happy with that. So if we put it into F-35 and give it just a little bit, what happens is all those angles, those IRTs shared across the networks and all the RF ones begin to intersect, and we're able to resolve them into locations. We may not have an ID in every one yet. You can see in the back, they weren't emitting, but they were hot, so I was able to put range on them. So the pilot begins to see where everybody is and what the environment looks out against. This is the power of being able to add all the off-board data to your onboard data and leverage that spatial diversity and the ability to put them together. And so, although this is an ideal picture, this doesn't happen instantaneously. This is sort of what the system converges to. And so that's a real simple example, but the idea of showing you how the fusion of F-35 is different than what we've had on our previous aircraft. At the very end, since we're just about out of time, the key things, fusion allows the pilot to return to the role of the tactician. He can now fly the aircraft, decide what to do in the environment, and the system takes care of providing that data for him to better understand the situation and to be able to act on that situation. And there's a picture of one of our nice flight test patches. Unfortunately, I didn't bring one with me, or I would have given away for the first question, which is normally what I do with the first question.
Oh, good deal. I'm going to hold you to that now.
There are reflectors on them now.
Yeah.
And that's it for my presentation. I hope it made some sense and was useful to you. I'm open to any questions you have at this point.
Thank you. That was a great presentation. My question is directly relevant to a DARPA project we're working on.
Do we need to wait till after this meeting to ask it?
No.
Okay, go ahead.
So the FSIM is the
I'm familiar with
simulation
that, yes.
to what level of fidelity does AFSIM describe the behavior of the F-35 that you just portrayed for us?
In no way.
Okay.
AFSIM the way we use AFSIM currently is to do sensor modeling to support fusion testing, right? The AFSIM sensor models are are still more in the legacy sensors, some of the modern ones. So for our testing, for example, our sensor vendors deliver us their models with it. It has their software wrapped up inside. So I get a really high fidelity model of each of my sensors. And then we created this tool where we're able to recompile the true fusion code, recompile it onto the processor and run it on our desktop using those models. And so I have high fidelity sensor models provided by my sensor producers. I have the real code running. I have it set up where I can not only simulate, when I get flight test data, I can replay that flight test data back into my real code and set breaks if I need to, so I can actually debug the data with the data we just took off of flight test. Now, of course, because it's a closed loop system, I don't get the benefit of the closed loop decisions I made, but as far as the front end of fusion, the correlation, the estimation, the ID, I can pick those apart as well.
Okay.
And so we don't use AFSIM. It just doesn't have these. It has a general radar model, but that radar model isn't as sophisticated as the one we get for our radar. It has actually all the different modes and the ability to command like our real systems are.
Okay. Thank you.
We do use AFSIM a lot for our skunk work type things where we don't really have a sensor. And so we can use that as sort of a generic sensor to go off and do our things. But for this, we want to use sensor models as closely modeling our real models as possible. Yes, sir.
Yeah, sorry, just beginning of talk, but I was wondering about the types of the sensors that to do this data analysis. For example, what types of sensors are integrated in this as well?
So we may have gotten that right before you came in. So our sensor suite has 5 major sensors. It's a radar, an EW system that covers 360, an IR system that covers 4 pi stereo radiant around us called a DAS, then a FLIR that is our IRST, and it does both air and surface type pieces. And then we have a communication system that handles IFF, air traffic control, data links, etc. And so those are all the systems input into our fusion on the F-35. Does that answer your question, sir?
Yes, yeah, perfect. Yeah, sure. Thank you.
So a related question to that is you have these 5 or 6 sensor suites on each platform,
Yes.
each aircraft.
Yes.
And then when you can share that information with other platforms. Is that a fused information that is shared with other platforms?
Yes.
Or
We share the tier 1 solution when we share with other platforms. And so, but because it's all independent data, and I'm not getting that data through any other source, we can use the tracklets to turn it back into an equivalent measurement and process it like it's essentially a sensor. And so that was sort of what I call one of the decisions I'm very happy with that we made. It takes a bit to wrap your brain around it, but in doing so, there's a way to get back to measurement-like data to get that accuracy. Often the question I get is, what happened to tier 2?
I was going to ask.
Excellent. I always wait for that question. The tier, because these are built and it's easy to add additional tiers, each tier we can decide what goes into it. Tier 2 was meant to be the MADL network solution. So if I was going to jump from an F-35 to some other platform, I don't want to send it every airplane's raw data. Can I combine all that data that's still independent and provide it a track that still can be turned into equivalent measurements, but represents just one view of the environment? And so it was the idea of tier 2, we would combine all that data before it jumped off to another network. So you didn't have to process all my whole network of data individually. We could give you the sum data of it, still independent before you jumped off. And so once we wind up connecting to another link that wants to do that, that was the mechanism we're going to use. But it also allows you to build any sort of view you want. Maybe I don't want link 16 data in this view. You could create a view that does that. We have indigenous data links that we provide for certain countries. So we use these tier solutions to do that as well. So architecture is just a real nice way to decide how you want to group your data and how you want to display it. Yes, sir.
On the second last slide, so I have some questions to do sort of related to what we call probabilistic alerting.
You'll have to tell me when I get the second last.
Yeah, just the one before this.
There we go.
So from a pilot's perspective, they're looking at the white, I guess they're squares or triangles. Those are sort of unknowns.
The white squares are unknowns.
They're unknowns.
We know where they are kinematically, we don't have any ID information.
And so are there any kind of procedures, philosophies, rules, policies on how the pilot should treat those?
Yes.
Do they treat them as red?
No. So no is a snap answer.
Yes.
That's the wrong answer.
Understood.
Uh,
It's probabilistic.
Well, it's not probabilistic. There are other rules that the pilots have. There can be safe corridors that if you come through this corridor with these characteristics, we will treat you like you're friendly. If you come on a corridor that's not one of those, we will treat you suspect. Even though the system will turn you yellow, the pilot will say you're outside of where you're supposed to be. Friendlies know they're supposed to come along this path. And so there are all sorts of procedure rules, as well as these handle the rules that are based on ID attributes or other things like that. You have the right IFF. You don't have the right IFF. You have an emitter on you that we consider hostile. So these type of things represent the things sensing can tell you. There are also procedural things the pilot has in his mind about where you come from, the route you take that may also lead into this. That won't show up in this display.
So inherent to this design is it took an uncertain environment and it converted it into red, green, and white.
Yes.
It took all the uncertainty out.
Well, these aren't 100%.
Yeah.
Some of these will have some ambiguities depending on what the specific emitters are or the specific platforms.
Can you say a little bit about the design philosophy to hide some of that uncertainty information?
So,
Sorry, that's the 70% accurate is better than a 50% is better than a 30. And why not share that?
so we actually share, if you go down into that box we popped open, we'll share probabilities down to some small level. We don't change the symbology till it hits some level. For ROE, for turning it red or green, the pilot sets a threshold that says either I want the ID to be greater than, let's say, 70%, or I have these following sensors of greater, and it sets a percent it wants in each of those. And so there's a percentage where the color changes, where the system automatically will change display. But anytime you can see what it is, if you open that box, that thing will say, well, right now it's 60% this, which may not be enough to change the symbology, but will tell you what that is. Now, the pilot's really busy, so normally he only digs down there when there's someone he really cares about that's unknown. He wants to know, why is it still unknown? Okay, it has a probability, it's just not high enough yet, or it's got a split between two guys, and he may have other information in his brain that knows how to resolve that.
So it's pilot's discretion.
Right, the pilot sets a threshold of where these things change colors. The system figures out how well it knows and reports that. And the symbology is all determined by the ROE, which are the rules the pilot programs in the airplane before it takes off. Fusion tells, here's where I think it is, here's how well I know that, here's the idea I think it is, here's the probability associated with all this. So then the pilot sets those thresholds. Well, actually, the squadron commander sets those thresholds.
Okay.
It's not individually pilot. There's the smart guy, who sets it for everybody.
So he comes in and there's an upload
Yeah.
of some sort.
Yeah, because remember, these are legal rules. And so there's lawyers involved with choosing this. And so each pilot doesn't get to choose his own. There's a standard load for this engagement today. And we allow them to store up to 5 different ones in there. So I didn't get to talk about the RE, but there's actually a real complex way to set these up to look like our legacy jets, to trust Fusion completely, which in many cases they just do that, or to have multiple ones at once. We have trust Fusion of this percent or the following sensor combinations. But all these things are set up for the squadron, and they are programmable from day to day.
I think here we're only looking at a static picture. We have to kind of imagine this as taking place at a very high speed, close to
Exactly.
supersonic speeds, even right at that point. And all of it is dynamic. The targets are also moving. The aircraft is moving.
We're closing quickly.
Yeah.
You have a Mach 1.5 up to Mach 3 closure.
Yeah.
Type thing. So things are happening very fast. Yes, sir.
So just a follow-up, just a comment. In our research, it's funded by NASA for civil aviation purposes. The philosophy is that the manufacturer needs to establish those thresholds, and that they're not programmable by an airline or in the field in any way. I just kind of make that observation. It's very contrasting.
Yeah,
And for
I have a
safety,
follow-up on this. Yeah, so it's a follow-on on Len's question. In the design process of the data fusion, how do you ensure that the fighter pilot will not get overwhelmed? I mean, what time of a prior knowledge you assume that the pilot will have on the system to make its decisions?
So we have, the pilot has the ability to select how many targets he wants to, or she wants on her display, as well as what mix. So you can say, I want the top 10 ground sites, the top 40 aircraft, and you can actually adjust those. And so there are ways first to control how many things are on display and what the mix of air and surface are. We also have layers where you can remove classes of targets. For example, on one layer, he dials a switch and removes everything that's civilian or non-threatening off his display. And so he has different ways to have the information presented to him. We call them layers, where he or she can readjust what's there to present only the things relevant at the time. If you're about to engage something on the ground, you can roll back and just have the things in that general area that are threatening to you and that ground site, and everything else off your display for the moment. And then roll back out to more situational awareness as you come up from that. Doesn't change anything under hood with Fusion. It's just managing that complexity for the pilot.
I have one question. I think I found it really interesting. You're incorporating this system onto like a stealth aircraft. Would the system also be able to understand what it's emitting and how that plays into the aircraft's stealthiness?
Yes.
Yeah.
The pilot makes instructions about how stealthy the pilot wants to be, and then the system respects those boundaries. So if the pilot says don't transmit anything, we don't transmit anything.
Gotcha.
We have a question from Ryan online.
Just a curiosity, how does the system react if you lose one sensor, has a radar, for example?
So the system is tolerant. We use whatever sensors it has. Losing radar would sort of be in like going MCOM, where you're not allowed to transmit. And so you normally have other ways to get information. If it's just you, you may rely heavily on your wingman providing you a lot of situation awareness. We have air to surface modes like a SAR map, where I need to go and use all my radar timeline to go and locate something on the ground and ID it. So often during those times, my wingmen are providing me all the air trails while I'm doing it. That's the advantage of working together, is everyone doesn't have to do everything. One of the things that I've been publishing on recently, and our STIG-MERGI stuff that you've heard a lot about, is how do we balance that so everyone's not tracking the same target with their own radar, but how do we let one person do it and let the other one go off and do other things? And so we've come up with these techniques for doing that are based on how animals communicate. They're very simple, they find structure very quickly, and they're very robust. And so some other time when I come back, we'll talk about STIG-MERGI. But it's a way to do that and then to adjust. If someone loses the radar, or if someone needs to go do a SAR map, the other guys step in and retake over and fill those gaps. So it's a way to optimize across your whole network, so you're not wasting resources.
Right, Ryan, you have a hand raised. Would you like to ask a question?
Yes, I dropped a couple questions in the chat. I guess the first one, it's really interesting to see all the various sources of fusion you have. In the satellite tracking world, one of the things we tend to do is fuse a lot of data from various sites to get an orbit track on something. Though sometimes, the quality of that data coming in from one site may differ than from one from another. So sometimes it's more beneficial to us to reject certain observations to get a better satellite track overall. How does the system here address that? I might be getting different wingmen in different positions with different qualities, say coming on the SAR map or getting detections from one of the other sensors. Is there a way of assessing that quality or confidence, and how does that get mixed into the overall picture?
Okay, so let me answer that in two pieces. First, from our onboard sensors, each sensor system has its own accuracy. And so normally with its measurements, I get the measurement accuracies as well. So I understand what the measurement was and how good it was. In most cases, those will be good enough to fuse into my system. I have a couple cases where they're not. I have very rough lines of sight. And so normally they cue other sensors to go provide a more accurate look at that data, so that it does get a quality that I can correlate into my system and fuse. Coming across from my wingman, then I get the track, but also get a covariance with that. And so the covariance then tells me the quality of tracks. Normally, because they're working with the same sensor set I am, it would be very rare for me to get a track from a wingman that I couldn't automatically fuse in. Now I may get a tier 3 track from my wingman that's from link 16 that's very poor. And so I recognize that. And so that now doesn't go into the fusion piece. That becomes a queuing cue for my sensor manager to say, if it's a track I don't know about, we'll provide that initial track by itself with this very poor quality sensor manager looks at it and says, well, that's not good enough. It starts queuing sensors out to go find that track and resolve it. So it becomes more of a queuing source if its accuracy is poor. And things that can cause that are latency. We talked about that earlier this morning. And sometimes it's a bad measurement. You know, it's an awkward observation. And so maybe it's good in azimuth, but it's coming from someone else. So it looks like this huge region of uncertainty when you receive it from link 16. And so those become queuing sources.
So you have competing objectives between the desire to be stealthy and the emissions that are required to detect. How does that get managed?
The pilot decides how active he would like to be, and then we exist within the rules that he gives us.
So, but if he asks for more information because something can't be resolved, you just tell him you're gonna have to change your rules on stealthiness?
He has a dial. He can choose between 5 different modes.
Okay.
And so once he selects the posture that we're in, we're limited by that. If he wants to exceed that, he has to roll his mode up a little bit to be more permissive.
Okay.
And each mode is not, you can't do this in this mode. Some are, you can't do background searches in this mode, but you can do other things in this mode. So these are very selective about what can be done and for what types of targets. A shootless target may be able to do something in the MCON mode that maybe you couldn't do for another target. So
basically in training, they become more familiar with what they're not going to know if they're trying to be stealthy.
they understand where they want to operate and they understand how to operate in those modes to get what they want.
Great, thank you.
We give them a lot of flexibility in their design of those modes. So their big brains can figure out what's the best way to suit our mission. And those MCON modes are programmable.
Great, thank you.
Charles, would you like to expand onto your question? I see a chat comment from you on, so it says, form beams wherever it needs it. Does that imply that it's based on active glimpses, based on assessment of the current situation and info needs, or?
What is this referring to? Just the active radar?
Yeah.
I think Charlie's on.
As you went on, it sounded like the system really is making a priority queue of what to look at next. So I assume it's choosing where to direct the beam-formed radar. Is that a value of information calculation, or can you tell more about that?
Yeah. So the way we sort of divided the labor between the sensors and fusion, the sensors start with their background volume searches. As they find things, then we may tell the sensor, go ahead and keep tracking that, and we tell it the quality we want. Sometimes it's just track maintenance. Just don't lose the track, but we don't really care about the quality. Sometimes it's weapons quality. We need you to bring up this quality. Sometimes we tell it, don't spend any energy. We call that search only. If you happen to revisit that search enough to keep the track, that's great. If you drop it, that's fine. The system has someone else taking care of it. I don't want you to spend any extra energy doing this. And that way we can move tracks around between sensors. But the general way we discover things is one of the sensors detects something. And so we get a line of sight for heat, or a line of sight between emission, or the radar will catch something. Once we have that, then we say, okay, I have a line of sight, I need to get range on that. So the first thing I'll do is I'll cue a radar, for example, over to say, okay, go down this line of sight, see if there's a skin echo from that line of sight. And then over time, I can combine those into a ranged track with the angle only data. But these are just, these cues are just interleaved with all the other things the different sensors do. So they can go quickly to do a target update back to the background volume search, update 2 more targets, go do a search over here. And because there's no mechanical movement on the radar, these things switch within fractions of microseconds. So it's very easy to go from anywhere in its field of regard to anywhere else instantaneously. But normally some sensor discovers it, and then all the other queuing is based on refining it, bring it up to the kinematic accuracy we want, and bringing it up to the ID content that we need. And we don't really tell the sensor how to do that. We tell it, once it detects it, we tell it if we want to keep tracking it or not. And then we tell it what accuracy we want. And the sensor takes care of knowing when to revisit that target. If it's flying flat and level, it won't revisit that target very often. If it's maneuvering or turning, it's going to update it more often to maintain the quality it wants of that, to make sure it doesn't lose the track. Does that answer your question?
Yes, it does.
So instead of a value of data, we are trying to bring each track up to the required accuracy and content, kinematic accuracy and ID content, in the priority order of the tracks. And so that's how we decide how to go spend our different sensor timelines. We also have mechanisms for moving tracks off heavily loaded sensors onto less loaded sensors. Normally the radar is most overload, so if I can get another sensor to take over the tracking load, that's great. If I get my wingman to take over the tracking load, even better. But the idea is, how do I maximize the sensor timelines on my aircraft and then on my flight, so we get the maximum capacity we can out of it. Always trying to squeak a little bit more.
As a follow-up, when you're coordinating among multiple aircraft, let's say they get far enough apart that they're seeing really independent things and they're not sharing information for a while. When they come back together, how do they negotiate so they don't just dump all their information at each other? Is there a way of saying, here's what I need to know?
So our data links are such that we're always in contact with them. I don't want to give numbers, but when you fly a flight group of 4, it would be almost unthinkable to get far enough apart where you weren't still linked up. We do have different perspectives, and they will see targets other people don't see, but in general, a lot of the environment field of view is just shared because the sensors have such great range that they overlap sensor coverage as well. And we share hundreds of tracks per second each aircraft. So just think flight group of 4, a lot of data flowing back and forth, always there. But if for some reason we get out of link, when they rejoin, they would begin to report that those hundreds of tracks, and we would just all take that information and begin to share it.
There's one more question from Arturo.
Yeah, just a little bit of a follow-up. You may have mentioned it, and I may have not. I have gotten it quite clearly, but you said that there are 2 ways in which some of the track data can be prioritized within a queue. One being the whether there's an overload within one of the resources, and the other one is whether or not the track itself is not well known. So does this prioritization have a multi-objective flavor to it? And if so, how, is there a preference for these kinds of prioritizations?
So I'm not quite sure I can remember the comment I made that generated your question, but in general, there is a single priority system on the aircraft that establishes how you rank a track coming in. Every track has its own ranking. It's a series of what we call bins you belong to. You belong to the highest bin you belong to, and inside that bin, there's a way to sort you inside there as well. And that governs the priority of your track, and that talks about what access we have to bring that track up to quality. And as long as we have sensor resources, we'll work as far down that list as we can. At some point, we may drop off. We may not lose the track. We may not be able to bring it up to that quality if we run out of sensor resources and off-board data isn't available to supplement that. But again, we're kind of working off that main priority list that's based on a whole bunch of different things. Some are pilot actions. For example, if he puts us in shoot list, it's very important. Some are based on the lethality of that track, its ability to hurt me. And things that can hurt me are a little bit more important than things that can't hurt me. And so those all feed into how things are prioritized. And I won't go
That's
into
really
those
interesting.
algorithms, but in general, pilots really care about things that can hurt me, that tie up on their care list. Other things are just navigation hazards or
All right.
points of interest as you fly by.
Thank you.
Sure.
All right, and I see a comment from Brian Burke. I see you're still online. If you wanna ask that live here on Zoom. So the comment from Brian is that often in the case of unknown context, fighters can be tasked with visual identification, and each combat theater has extensive rules of engagement that govern how the fighters can handle various contexts. Basically boils down to, can I shoot it? Shoot it.
Oh, we're now past the visual ID. If you're making visual ID, you already failed, and you're probably not alive still. Because starting with the F-22 and before, the idea was you can engage before they ever know you were in the neighborhood. And so the idea is you're stealthy, so you're harder to find, but your sensors are reaching out so much further that you're able to engage someone before they ever know that you're even in their neighborhood. And so that is really the power of having a stealthy aircraft plus having sensors to reach out very far, is the ability to understand the environment way out before they ever could detect you or even know you're there.
I think we're almost getting to time. I'll ask one more question. So you mentioned about Dempster-Shafer theory, right? And so Jack's probably learning about Dempster-Shafer right now in one of the fusion courses.
I'm sorry. It takes a bit to wrap your brain around it.
Yeah,
He's the professor for that.
and so you mentioned about moving away from belief masses and using probabilities.
Yeah.
I was curious to know why that was the case.
Yeah, if you can say some, say some more about that.
So the idea is there's still belief masses, but if you can state them as probabilities, then you're actually making an estimate of the true probability of each of the drawing a blank. It's the hypothesis.
The hypothesis, okay.
Right. And so one of the things, and I didn't mention this, but one of the innovations that Kent made is we use the ID data in the correlation decision. Before we'll do a correlation, we have a set of feasibility tests. And so I have a new measurement. If there's any ID information with it, or the thing I'm going to fuse it to, it goes to a series of questions as, is it feasible to put these two IDs together? And if the answer is no, ID will not let that correlation happen. And so it prevents some really bad decisions just because they're close to each other. And so we can get two emitters to come real close to. We can use the emitters to pull across things where the radar collapses into a single track. I can still tell there are two tracks there, and I can hold them apart when they come back out of the merge. And so the ID helps, feasibility tests help me from making a bad correlation decision that's not possible. It also prevents some of the pathological cases you get Dempster-Shafer, where you have this real unlikely case that all of a sudden becomes the only case that's possible. It's like you handle your correlation well, it'll help you all the way down the path. But yeah, that was the great thing. That allowed us to display probabilities to the pilot, and it's very useful to them, the ability to understand how well, because before they had no idea of how well. It's just fusion finds that's bad guy. And the pilot had no input to where that threshold was. The designer got to say, here, we can tell you how well, let you set your own thresholds for when you're comfortable with it.
Yeah, and probably I think the language of probability is better than using belief mass or plausibility, which is very common in Dempster-Shafer theory.
Right.
And that could confuse the pilot or make them lose trust
in
the system.
Tell them belief mass, they look at you kind of funny. You tell them probability.
Yeah.
They kind of, that all makes sort of sense. There are many people who tried to implement Bayesian systems. The problem is you're just kind of guessing at the a priori statistics. And so that bias, kind of peanut butters all your solutions. And so Dempster Schaefer seemed to have seems to have worked out very well for us. So Kent got a gold star for that.
All right, so maybe I think in one of our lectures, I'll invite Kent next time.
It would be fast. He's an MIT student as well, and so he knew some of the different people who start on a theory. He's be fascinated by him. Well, thank you.
All right. Any other questions? We're almost over time. I'd say, let's take a, both a in-person, real, and a virtual round of applause for Dr. Frey. Thank you for your sharing your thoughts with us. And any closing comments? Going once, online, in person, here?
Well, I wanted to say thank you for an excellent presentation. I really enjoyed the use case at the end. So those of us who are not working day to day with tactical fusion, it really illustrated some of the concepts that you're talking about.
Thank you.
All right. Thank you for everyone on the Zoom for joining us. I will end the session here. And as a, the talk is recorded. If you would like to view it again, we will share the link as well.
Thank you very much.
All right. Thank you all for joining us.